And our last speaker, it's my great pleasure to introduce Professor Dimitar Grantcharov. He is a mathematics professor at University of Texas at Arlington, USA. He will talk about the weight modules of Lie superalgebras at infinity. Please welcome, dear professor.
Thank you very much. Let me first thank the organizers for inviting me to this nice venue. It's a great opportunity for everyone to meet although online, but still to discuss superalgebras and related topics. My talk is based on a joint work with Ivan Penkov and Vera Serganova, and the work is available on the archive. Let me mention that it was a great pleasure collaborating with them. It was like my old dream that came true. There was a slight problem in a good sense that one of them kept asking questions and the other one kept answering. So as a result, the paper has quite large number of results. I'm not discussing the quality. I'm not in a position, but today I will focus on two aspects of our work, namely modules over Cartan type and Weyl type and Clifford type superalgebras and orthosymplectic superalgebras. And for the special linear Lie superalgebras, I will certainly have no time, but there are quite a few results in our paper. So let me briefly go over the conventions and basic definitions, taking advantage that this is the last talk. It is great that I don't need to introduce much. So ground field will be complex numbers. We can easily extend the results to algebraically closed field of characteristic 0, but complex numbers definitely would make everything much easier. The parity functor will play some role in future, although it's not super important, but we will have to mention in few cases up to parity, as you will see. Then we will, as I mentioned earlier, focus mostly on the orthosymplectic superalgebras, but we'll say a few words about GL and SL. The important part of the talk is that we allow A or B to be infinity. So I'm not defining OSP infinity, 2B, and so on. These are understood as direct limits, and you can choose any embedding, for example, upper left corner, depending, of course, on the case, which is infinity, A or B. We assume all homomorphism to be grading preserving, and we fix a Cartan subalgebra or Cartan subsuperalgebra. So in this case, OSP things are quite nice. We don't have odd part of the Cartan, so no need to work on this theory of modules over the Cartan, like in the, say, the queer case Qn. And on the bottom of this slide, for convenience, I listed the weights of the standard or the natural or the defining modules of the superalgebras that I mentioned, GL and OSP. And I'm using this slide to say that by support, I will mean the set of weights, namely elements in the duo of the Cartan for which the corresponding weight spaces are non-zero. So on the next slide, I will give some brief history on simple weight modules of finite dimensional reductive Lie algebras, leading to a famous result of Olivier Mathieu. First, a definition that luckily most of you know very well. A weight module is a module that decomposes as a direct sum of weight spaces. If we require, in addition, the weight spaces to be finite dimensional, we will call this weight module of finite type. This is something that will not appear much in this talk because the talk is based more on the so-called bounded modules, namely those modules of finite type that have this additional restriction that the set of weight multiplicities is uniformly bounded. So there are many reasons to study this special category of weight modules, and one of them is this nice description of Olivier Mathieu back in 2000, that the simple bounded weight modules, and this is in the case again of reductive finite dimensional algebras, and again we talk about complex numbers as base field. These bounded weight modules come in coherent families that in most of the cases, like symplectic and special linear algebra, most of the cases have nice geometric realization. And we present the elements of the algebra as differential operators, so the corresponding modules are modules of sections of vector bundles. And the good news is that when we try to somehow extend all this work to the case of direct limit Lie algebras or superalgebras, not many of these simple bounded modules survive. Namely, many limits of simple bounded modules are modules of infinite type. So that's really nice. So somehow in our study of bounded weight modules, we limit ourselves to the best understood modules for these finite dimensional simple Lie algebras or reductive Lie algebras. And also, it's good to mention here, at least in some form, the result of Mathieu. And I'm using one statement that I will not use later, but it's important to know that these bounded weight modules, as well as any simple weight module with finite weight multiplicity, is also a twisted localization of a highest weight module. So we have some kind of geometric description on one hand and algebraic description, if you wish, on the other. And it is nice to note that immediately that these bounded weight modules over Lie algebras and superalgebras are those that correspond to weight modules of finite type over the corresponding algebras of differential operators. So one more reason to focus on bounded. I mean, they are nicely related to modules over algebras of differential operators. And here at the bottom of the slide, I stated the obvious goal in our paper and in this talk. We want to study category of bounded modules over any of the direct limit Lie superalgebras I considered. And let me mention immediately that in a way the category of bounded modules over a direct limit Lie superalgebra is way easier than the finite dimensional reductive Lie superalgebra case. So when one of the numbers A or B is infinity, especially in the orthosymplectic case, it is easier to somehow get grasp of the category. So we have here two important algebras we can call these algebras of differential operators, but that's another story if the term is correct. We have two important associative superalgebras that are related to the Lie superalgebras I mentioned. So we have the Weil type and the Clifford type. And again, we allow infinity in both directions, like for even and odd variable. And we have two aspects of the theory, like what we assign as even and odd variables and what the relations are. So if the relations and the even and odd variables are related to the Lie super bracket, we will have Weil superalgebra. And we have here the odd variables to be indexed by negative numbers and the even variables to be indexed by positive numbers. So 0 is excluded. And if we associate the relations to be somehow anti-bracket, like not the Lie super bracket, but the like Lie anti-super bracket, then we have Clifford type. And again, if we allow infinitely many even or odd variables, we index them with positive and negative integers, we have this general Clifford superalgebra. So this was actually considered earlier by Jonas Hartwig and Vera Serganova in a paper. In our work, we somehow extend this to infinity and take advantage of this general setting and somehow separate everything into two parts. So again, x and d, like x ddx versus xi and eta xi and like dd xi will be the variables for the corresponding algebras. The index is non-zero. We have also natural Z grading in both of them, in addition to the Z2 grading. So we have like three subalgebras associated to D and Clifford, and each of them is different from the other, like the purely even part, the degree zero part, and the sum of all even degree with respect to the Z grading. And each of them actually plays important role later. And if you want to have some isomorphism between the Clifford and the Weil algebra, we do have, but just a warning that the parity is important. So for example, one may naively think that Clifford 0b is related to db0, but it is not. We need to change parity, and this is the idea of this dagger that actually will not be involved later. So I'm just mentioning this in case a measure question is asked. Don't we have some obvious isomorphism? Yes, we do, but we pay the price with this dagger. And we have more isomorphisms in terms of tensor product, but this dagger should be involved. Okay, so now it's time to go to the first homomorphism, and you see this change. 2b2a corresponds to ab. So the first homomorphism is from the orthosymplectic superalgebra to the Weil superalgebra. So this is not a new homomorphism, but in a way we put together everything. We allow infinity, and we have two important homomorphisms for OSP2A to B. One is for the Weil, and the other is for the Clifford. For the Weil, the things can be explained invariantly through the even anti-symmetric non-degenerate form. So if we use this form that defines OSP in a way, then we naturally define this homomorphism of associative superalgebras. And again, 2b2a is what we have naturally. And if we want 2a, 2b to go to ab, we will need to use Clifford. So I'm rushing a bit here. So you either haven't seen this and you will need to kind of spend some time to convince yourself, or you know it and you're probably angry that I'm spending time on something obvious. So I'm doing something in the middle. But if you feel uncomfortable with this fast invariant definition, I will give on the next slide explicit description up to a scalar multiple of these homomorphisms. And this is the slide. So for example, if you look at this, you see kind of something that you have seen before, the element with root epsilon k minus epsilon l goes to x minus l d dx minus k, and so on. Again, this is up to a scalar multiple. So if we want precise constants, it's a bit annoying. We need 1 over root 2 and things like that to be involved. And anyway, the good news is this don't look very nice, but once we switch to OSP odd even, the fact that we have odd roots of the form like epsilon k delta k makes everything nice in terms of this explicit realization, because once we define a natural homomorphism from OSP to A plus 1 to B, it should go to the Clifford first. And second, we have this very, very nice association. So, and it took us quite some time to make sure we match the roots, like that eta k should correspond to epsilon k, ck to minus epsilon k. So we made a few mistakes that come from some intuition. So the intuition works in both directions, and how it gives you some general idea, but also it leads to some easy mistakes. So again, this is roughly how the roots of the corresponding Clifford elements look like. And now I'm switching to the representation. So in the next few slides, I will discuss the weight modules of Clifford and Weil superalgebras, and then I will use the functors to define corresponding bounded modules over OSP. And first, and kind of most important, we have natural modules over Clifford, sorry, over Weil, natural modules over Clifford. And in order to make the modules over OSP, we will notice immediately that they are not simple, namely the module of all polynomials is a nice module over the Weil algebra, superalgebra, but it splits into direct sum of 2 when it goes through the homomorphisms. So for this reason, we have even and odd 2 natural modules over OSP, other 2 natural modules over OSP through the others, the other homomorphism, plus their parity changes. So we have like 4 natural modules over OSP, 2A, 2B, and then we have this definition of spinor oscillator. So these are in general infinite dimensional modules. Okay, so in case, for example, B is 0, they may become finite dimensional, but these are infinite dimensional. And here is in case you want to know the highest weight. So they do have highest weight, but we need to define Borel. And again, we end up with quite some modules. The good news again for OSP odd even is that we don't need to split the polynomials into two parts, right? Because lambda xi becomes naturally a simple module over this. So in this case, the spinor oscillator representations are just two. And again, we have nice highest weight. This module in general is infinite dimensional. And notice that A is possibly infinity, and the weights here, therefore, may be some infinite sums of epsilon I when we consider weights. So A will stand for DAB or Clifford AB. And let us now define the notion of a weight module over A. So we need to define something like Cartan, and it is natural. Consider some elements like xi, ddxi. Then HA star is quite large in general because A and B can be infinity, right? So HA star is something of cardinality Aleph 1, not Aleph 0. Aleph 0 is for H. But for the weight, we may put additional restriction that when we act on this, for I negative, we have 0 and 1. So the set of weights is not the whole HA star, but it's not a vector space either. This makes our kind of consideration much easier then. Then we can define a weight module with the aid of this HA check. Support comes naturally. The root lattice, though, is something which is direct sum. So once again, HA star is direct product, but for the roots, we need finite sums. So when we have root lattice, we want direct sum. So direct sum in direct product, that's actually very strict embedding. Then this is something which may look very abstract, but it is quite convenient if we define a parity function on the root lattice, something which is sorry, not on the root lattice, on the weights, something which extends the parity function on the roots and on the root lattice. And in order to avoid all this drama about up to parity change, we decided to introduce the notion of preferred weight module, namely a module which has this natural definition. A weight space is purely even if the parity of the weight is 0, and purely odd if it is of weight 1. So this immediately leads to a nice result that a weight module is direct sum of prefer and like parity change of prefer. And with this in mind, we have a natural notion of preferred weight modules, like half roughly of the weight modules. And here is our first result. Classification, but this is not the best classification. We have better classification in our paper, but classification in terms of parameterization of simple weight modules that are also preferred. And the classification is up to kind of not classical, but standard equivalence relation. So this equivalence relation, in case you have seen classification of simple weight modules over Weil algebras, this is something definitely not new. Somehow we first relate them through the lattice, and then we somehow keep the non-negative integer signs, non-negative integer components of the weights the same. And this, by the way, extends our result with Slava Futorny and Walter Mazurchuk on D infinity 0. Okay. So this is the first result, and here is like the more general result, how to treat the whole category. And no need to read carefully everything. In short, the category at the end of the day is somehow a direct sum or direct product of categories over dA0. And again, dA0, this is purely even while associative algebra. The case when A is finite number is well studied before, and the case when A is infinity is in our paper with Slava Futorny and Walter Mazurchuk. So we did reduce the study of WA to something which is well understood already. And now at the end, I will connect this theorem with the bounded modules over OSP. So first of all, we have notion of spinor oscillator type, a module which generalizes spinor oscillator representation. Namely, if we have a pullback of a weight module, so not necessarily polynomials, but we may have some kind of shifted polynomials. So this is where this classification over Clifford AB in a way comes very handy. So spinor oscillator type is some nice generalization of spinor oscillator representation. And the first result is that if we have simple bounded weight module over G, it is either this spinor oscillator type or variation of standard or trivial. And this makes everything nice because we are now in a position to give quite nice classification result of the simple bounded weight G modules, because we need to focus on the spinor oscillator type. And then we notice that these modules somehow come in these twins. So first we have that both the degree 0 and degree 1, the even and odd part of the module are simple over G0. And then we have this very nice description of the even and odd part somehow there of this form S tensor T, and S and T are related to S prime and T prime through the so-called twin construction. Like the even polynomials are like the twin of the odd polynomials, roughly. So we have pretty good description, if you wish, of the simple bounded weight G modules. And it's important to note, I didn't say this, but one of A or B is infinity. Otherwise, it's way, way more complicated. And at the end, I will give a general result on the category. Category of bounded weight modules over orthosymplectic superalgebras at infinity. So we have bounded modules of oscillator type, and bounded modules over A. So bounded modules over A is almost like weight modules over A of finite type. I mean, the simple objects are the same, the decomposable objects are the same, but when it comes to direct sums, we may have some weird differences. So, and this is the theorem, that this is equivalent to this, or to this, you see this A even, and therefore we somehow transfer the study of bounded modules over orthosymplectic algebras to weight modules of finite type over algebras of Weil type or Clifford type together. This together with the result on classification of this simple weight modules over A and description of the category, at the end of the day reduces in a way the study to these modules that were studied in papers that I mentioned already. So again, there is something on GLSL that I will skip, and that was all. Thank you very much.
Thank you, dear Professor Grantcharov. We will go ahead for questions and comments. Please.
One question.
Welcome.
What happens when A and B are both infinity in the case of OSP, the odd even? Well, I guess it doesn't matter as much, but is there much to be said already, or is that something next?
Yes. So again, this depending on the case, we have simple modules and study of the category. The simple modules are very pleasant because when we have like even and odd and even, first of all, we have the standard modules, right? And then when we come to this, we have this part C. That's very nice because we don't have to pair roughly S with S prime. This is because in the case of like odd infinity, the polynomials come as simple modules. So we don't have to have even and odd. So this is probably one of the most pleasant cases. OSP infinity, but like odd part.
More questions? Okay. Is there anything else to cover? You want to cover, dear Professor?
No, maybe just for fun, here's some isomorphisms if you wish to involve the dagger and have fun with that. I mean, if you want to study Weil Clifford versus more standard Weil Clifford. Yeah, thank you. One last thing. Being the last speaker is my honor on behalf of all speakers to thank the organizers for organizing this nice conference. So
thank you.